Okay, welcome everyone to this continuation of what is tropical geometry. Today I would like to talk about polynomials, but not just polynomials. Polynomials are too boring, I'm going to talk about tropical polynomials, which are easier than polynomials, so in that sense they're even more boring. But anyway, so algebraic geometry should be about polynomials, not just should be. Algebraic geometry is about polynomials. Albeit in a potentially hidden fashion. So sometimes if you just read algebraic geometry, you can't see anymore that it's about polynomials, but in reality it is about polynomials. So tropical geometry should be about tropical polynomials, yeah? Makes some sense? Maybe in some universe? Well, I hope it does, because that's what we're going to talk about. So tropical polynomial. Well, what could be a tropical polynomial? Well, I kind of want to make the difference here between a usual polynomial and a tropical polynomial. So I just pull up a usual polynomial. Usual polynomial is a polynomial as you know it. So here's a polynomial, and let's say we have two variables. So I can see that as a function from r squared to r. So I'm still a big fan of. I know it's not open access, so I shouldn't use Mathematica too much. But somehow its plotting abilities are pretty good actually. I somehow like that. There are certainly open access version options that you can more easily access. So it looks like a parabola type thing, very like smooth. So here you can kind of see already some kind of a parabola type object, yeah. So a classical polynomial. So kind of see the parabola here in x squared. And Wikipedia tells me or told me when you're watching this, it might have changed because Wikipedia changes, and that's totally fine. That's kind of part of the game. But anyway, in March 2025, when I recorded this video, there was a sentence that essentially explains what a polynomial is, and it absolutely makes sense. So a polynomial is a mathematical expression consisting of variables and coefficients that involves only operations of addition, subtraction, multiplication, exponentiation. Wonderful. And all of this makes actually sense tropically, yeah? Instead of, well, do we know what a tropical addition is? Subtraction is a bit of a rule. We don't really know what that is, but we really don't need that all that much. We can put that in a coefficient, right? So whether you have x minus y, you can just say that's whatever. It's just x plus minus 1 times y, right? So you actually really don't need subtraction in that sense. But anyway, so everything of this makes sense tropically. And a tropical polynomial is just a polynomial, but replacing everything that you see for a normal polynomial with the tropical operations. So something like this. Exactly the same thing, seen as a function, right? So it's exactly the same, seen as a function from exactly the same. But the only difference is we replace now all of our things here by tropical operations. 2 tropical times x, tropical times x, and so on and so on and so on. And this really just means, so how does this work? Well, whenever you see a tropical plus, you just put a comma. Whoop, here's a comma. Tropical plus means a comma. And whenever you see a tropical times, you just make a plus. I guess this is a comma as well. So whenever you see tropical times, let's just do this in a slightly different color, maybe green. So whenever you see a tropical times, you just write a plus, right? So whatever, blah 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 blah. Let's just finish it. Why not? We have the time. It's a video anyway. If you don't like to watch me writing down plus symbols, you can just quit, I guess. That I won't blame you at all. I won't blame you at all. Don't worry. And now you can just write it down. 2xxy, 2 plus 2x plus 2y. Minus 1 y, minus 1 plus and whatever. And then you replace the outer thing by a min. And that's the corresponding function. And those functions tend to look like this. They have this piecewise linear shape. So I also did it here. So it's kind of a very different type of object. Looks more like a rooftop. And this kind of fun line here that you see in white is, so this is a plane, here's a plane, here's a plane, here's a plane, but the whole thing is not a plane. It's kind of multiple planes glued together along those little lines here, and the lines will play an important role. But now let's have a look. Smooth, piecewise linear. Smooth, piecewise linear. It's kind of the main difference between a polynomial and a tropical polynomial. Otherwise, really just replace the operation symbols. You know? Kind of really, really simple in that sense. And you can go really from one to the other, and essentially the process should be called tropicalization. Yeah, it's tropicalization will be something slightly different, so I will not say that, but essentially it should be tropicalization. Yeah? And the top curve here is the original polynomial x squared plus 1, and the orange curve, so the bottom curve, is the tropical one, which is x squared plus 1, which is just min of. And you again see the same pattern. It's like piecewise linear and with a breaking point where the other one essentially has its root. Yeah, if you just move that down a little bit. And tropical is really just replacing, really simple, plus by min, and multiplication, which I just wrote here as a circ, because otherwise it's not unable to see that. But anyway, multiplication by addition, and it maps polynomials to tropical polynomials. And maybe now you can see how you could, in principle at least, and you can, up to a certain degree, map algebraic geometry to tropical geometry by just replacing the corresponding operations. And yeah, and tropical polynomials isn't just an expression of the form as you would expect it to be, with some real coefficients. Yeah, and all the standard arithmetic works. Just be careful you don't have an additive inverse. Otherwise, these are just continuous, piecewise linear, and concave functions. So if you forget what concave is, you can essentially draw a line underneath, and here's exactly, that's why I call it a rooftop. It's like this nice concave type shape, right? It kind of goes like a rooftop. Yeah, it's kind of this concave type shape. And it's like very different from usual polynomials. So usual polynomials are not piecewise linear unless they are linear. So most of them are not. That's kind of the difference. So tropical geometry is really more about piecewise linear functions than like usual functions. And what we will study in algebraic geometry, you study the roots of a polynomial, and we do the same. But what we will call the roots is kind of the most interesting part of this curve. The most interesting part of this type of curve here is where the hyperplanes glue together, and that's that bit. So this little dumbbell type shape is what we will call the roots. In this two-dimensional picture, the breakpoints, right? So here's a breakpoint, here's a breakpoint. In between here, it's like this 2x minus 10. Here, it's I think it's just this one, and at the top, it's just this guy here. And where it breaks, we call that the roots. So this polynomial, written down here, this funny thing, has two roots. Yeah, and in general, those polynomials will have quite a few roots, but this is exactly what happens in algebraic geometry anyway. And we are going to study those types of kind of piecewise linear shapes that arise in this fashion. Anyway, I hope you enjoyed this video, and I also hope to see you next time.